So it's like different ways you can speak to a child based on the nurture of how they prefer to be spoken to, like bad things that they were always supposed to learn all of them.
Okay, we're going to get started. Grab a seat, please. Okay, so greetings and welcome to Lecture 10, Computer Vision. This is our last lecture together. Hope you enjoyed the module. Now, the story about computer vision isn't complete unless we talked about deep learning, and Slabaugh did a great job of introducing deep learning into this module a few weeks ago. We thought it'd be really helpful to actually dedicate the final lecture exclusively to deep learning. So we prepared this. Now, as you know, this lecture is not going to be specifically on the exam, but nonetheless, the material in this lecture may be very important to some of you, especially those who are going to explore deep learning in your individual projects. Okay, so just a quick recap from last week. Last time we talked about video and how you can load videos into MATLAB. In fact, MATLAB makes it very easy. You can grab the individual frames and then you can start analyzing using computer vision techniques. And there are kind of standard types of algorithms you might want to develop that work on video. One algorithm is motion estimation. So there you want to identify which pixels are moving. And also, once you can detect moving pixels, you might want to know where they're moving to. And that leads to optical flow. So in an optical flow problem, you're trying to find a vector field, which represents how every pixel is moving in the video from frame to frame. So we talked about different ways to estimate optical flow. In fact, I showed you 3 ways. And then we took a look at the KLT tracker, which is a very popular tracker for tracking specific types of features. And we said last time that corners are good features to track because they're distinctive and they don't suffer from the aperture problem. Okay, so today it's all about deep learning. And so you've had an introduction with Slabaugh's lecture a few weeks ago. Some of you may have attended the Databytes talk. I was here a few weeks ago also talking about deep learning. But in my talk, it was very high level, which was nice and kind of introduced the concepts. But maybe at this point, you don't have a real good feeling about how to actually do deep learning. So the point of today's lecture is to go a little bit deeper into deep learning technology so that you understand how networks are constructed in terms of their architecture, how you might train them, and how you can use them to solve all sorts of interesting computer vision problems. So we're going to go back and actually look at some of the techniques that we talked about earlier, like segmentation, like image filtering, etc. But we're going to recast the problem in the context of deep learning. So although the application might be familiar, the method might be quite different. So we're going to look at denoising, super resolution, and image segmentation. And in particular for super resolution, we're going to go into a bit more detail. Then I don't think I'll have enough time, so I'm just going to quickly cover semantic image synthesis, pose estimation, optical flow, and disparity estimation in a quick fire approach. So just a few minutes on each topic. So the idea is to go deep into some topics like super resolution and then broad across other topics so that you have a good feeling for how these networks are constructed and how you can use them in different applications. I'm also going to save a few minutes at the end of today's lecture to just kind of wrap up the module. Okay, so what is deep learning? I think you're all familiar with the concept now. Essentially, deep learning, you're using neural networks. And these neural networks have multiple layers of nonlinear processing for feature extraction and transformation. So each successive layer is going to take the output from the previous layer and then perform some processing on it. So the interesting thing about deep learning is that the features are learned. Okay? So in traditional machine learning, you might have a problem like this, where from an image of maybe there's a car, maybe there's not a car in there. You want to be able to classify that image as car or not car. And the way you might do that is you might first extract some features, and as a algorithmic designer, as a computer vision scientist, you might decide what types of features you're going to use. And then you feed those features into a classifier, which can then make this prediction. Okay? Now, I think many of you are, in fact, doing just this for your coursework in this module. Okay? So maybe as an algorithmic designer, you've chosen hog features to identify faces. And then you put those hog features into a classifier, like SVM, to identify the person image. But you have a lot of choices, right? Instead of hog, you could use bag of visual words, or you could use other types of features. What's different about deep learning is that the feature extraction is embedded in the network along with the classifier. Okay, so when you're doing deep learning, you're not handcrafting these features. Instead, they're being learned by the network itself. And these features ideally are going to be optimal for the task because you're going to minimize a loss, and when the network converges, it's going to be optimal for solving that problem. Okay, so you can use deep learning in lots of different problems, and in fact, you've seen it before for image classification. Slabaugh talked about that. He also talked about object detection, so you learned about things like faster RCNN and YOLO. These are very popular techniques in computer vision. You can use it for semantic segmentation, and I'll touch on that in today's lecture. Super resolution, okay, we're going to talk about that quite a bit. Here you're taking a small image and trying to make it bigger and have a lot of high frequency detail in that super resolved image. Some other topics could be image restoration. So here you have a grayscale image and you want to colorize it. Okay, maybe this is a very old photo and you want to know what it looked like with color. You can build a network to do that using deep learning. Pose estimation, I played a video clip just before the lecture where you can actually identify body parts and then track them through a video sequence. Here's another really neat application, it's style transfer. So here you have a picture, okay? And what you want to do is sort of transform that picture as if it was painted in the style of a particular painter, like Van Gogh. So you can actually transform that image and make it look like it was painted. So these are just some cool applications that you can use deep learning for. And we're going to cover some of these today. Okay, so when we're talking about deep learning, we're going to see a lot of the same types of operations again and again, depending on what network we're looking at. So one of the most common operations you're going to see is convolution. And in fact, you've learned about convolution. Slabaugh already talked to you about this. So in convolution, you have this kernel, okay? And you're going to apply it to an image. You're just going to overlap it with a part of the image and then perform multiplication and additions. And that will give you a number in the output, okay? And then you're just going to sweep the kernel across the image to get a whole bunch of numbers, and this is going to be the convolution result, okay? What's interesting about deep learning is that these kernels, the weights that are in the kernel, are going to be learned, okay? So you're not going to design the kernel yourself. You learned about low-pass filters and edge-preserving filters, etc. You're not going to do that. You're going to let the deep learning actually learn the convolution kernel. Another very common operation is ReLU. This is a type of activation which performs a nonlinear transformation to the data. And ReLU is super simple, actually. What it does is it just sets any negative values to 0. Okay? Any positive values, they retain their original value. This is not linear because you can see the curve, it's not linear. It's actually two piecewise linear segments, but it's nonlinear. And this nonlinear gives you a way to transform your data through this type of mapping. Another very common operation you have in deep networks is pooling. And here what you're going to do is you're going to combine a bunch of adjacent pixels to produce a single value, okay? For example, in this image, I have 1, 1, 5, 6, okay, in a little 2x2 sub matrix. If I'm doing max pooling, what I can do is take the maximum value of those 4, okay, and then put it here. And you can imagine similarly for these other regions, okay? So if you'll notice, what happened is the size of the image decreased. Okay, so we went from a 4x4 image, now it's 2x2. So this actually decreases the size of the image, and it allows the network to learn more sort of high-level or broader abstract features from the data. So an important point here is that when you're pooling, you're downsampling. Okay, the data is getting smaller. Okay, there's more. In CNNs and other types of networks, you might see dense or fully connected layers. These layers are designed so that all of the inputs are connected to all of the outputs. Okay, and these connections are weights. So here the weights are visualized with a different color, reflecting how strong that weight might be. So by doing these dense connections, you actually lose the spatial information in the image, but you're able to look at the entire image holistically. And so for that reason, you often see these things at the end of a convolutional neural network, where you want to aggregate all of the information that's come through the network and make some final classification, whether it's a dog or a cat or a boat. Another thing you see quite a lot these days are skip connections. So in a skip connection, what you're doing is you're passing data, usually feature maps, which are coming outside of your convolutional layers. You're going to pass them over parts of your network, okay? And it's been shown that this can help with back-propagating gradients. Another thing you might see is batch normalization. So here, what you're going to do is you're going to normalize the data going through a layer in your network. Essentially, you're going to subtract off the mean and divide by the standard deviation, okay? So you've kind of normalized the feature, and then you can denormalize when you come out the batch normalization. So by doing this, your layers are a little bit more independent of each other when you're training. Another thing you tend to see quite a lot is upsampling. So we talked about pooling, how it's downsampling. Okay, it's making the resolution of the image smaller. Well, at some point you might go back to the original resolution, and for that you need an upsample operation. And there are loads of ways to do upsampling, and in fact that could be a lecture in and of itself, is how to do upsampling in deep learning. There are really simple things you can do, like nearest neighbor and bilinear interpolation. There's this thing called transpose convolution, unpooling, subpixel convolutions, etc. I'll talk about this a little bit in today's lecture. Okay, so with that in mind, what I'd like to do now is talk about how you might characterize a convolutional neural network. So in computer vision, we're often dealing with convolutional neural networks. And the reason why we're doing that is because convolution is really well suited to image data. Okay, so in an image, you've got a lot of pixels that are right next to each other. And often there's a lot of correlation from pixel to pixel. So by using convolution, we can sweep a filter over the image, and we can extract meaningful features in a very efficient way. You might also see recurrent architectures for temporal data, like videos. Now, if you have a deep network, there are a couple ways in which you can look at it. One way is at the architecture. Okay, so the architecture is going to describe how the layers of processing are arranged and what they do. Okay, so here, for example, is AlexNet. You might have heard of this. This is a very popular convolutional neural network that takes an image that's size 244 by 244, puts it through all these layers, and out comes a classification label, one of 1,000 different categories telling you what's in the image. So the architecture relates to all of these layers in terms of what they're doing and how they're arranged. So these are all convolution layers. We've got some max pooling, some ReLUs. Over here are some dense layers. Okay, so you can kind of think about your architecture in the sense of how your algorithm is designed. Now, a convolutional neural network, it can be a classifier like AlexNet, where it's putting out a label. So here we transform an image into a label. But perhaps you have a regressor instead. So here you're going to output a floating point value instead. In fact, you can do that for every single pixel in the image. So you can transform one image into another image. In addition to the architecture, you can also think about the loss, okay? And this is a mathematical representation of the error that's produced by the network, okay? So when you're training your network, you have an input that you're going to push through in a forward pass, okay? And you also, in the supervised setting, have a label. You know the ground truth for this input. So if I've got a picture of a dog, I know I've got a dog when I get to the other side of the network. So I can push the image through the network in a forward pass, then I can check the actual classification I did. Maybe the network classifies it as a cat. So there's an error there. So I can take that error and then I can back propagate it through the network. It's going to update all of the weights. And by that way, I can train the network just iteratively until it converges. So when you're talking about the training, you also want to think about the data that you're using to train, okay, and the optimization strategy. And in fact, this is probably the unspoken dark truth of deep learning, is that data is so important for building these types of networks, okay? So if you're a computer scientist, you know, you're working in industry, you know, you might want to design loads and loads of networks. It's lots of fun. But until you have data, you can't really train your network. And often, you know, building these types of networks comes down to a problem, really, of data collection. How do you get that data? How do you put it into a format that your network can understand? How do you deal with the noise that's in the data? How do you clean it? How do you pre-process it? These are really important operations that you need to consider when you're building these types of systems. Okay, any questions with that? Okay, so what I'd like to do now is, oh, sorry, do you have a question? Yeah.
How is this different from multi-layer neural network? It's like you're just coming up with some filters in there, which are like different layers. So
yeah, I mean, this is a multi-layer neural network. So it's maybe a subset of the broader scheme of multi-layer neural networks. The big difference here is we've got these convolutional layers. And essentially what you have in these networks are filters that you're going to apply to the image. And here actually in AlexNet, you see this 96 here. What that means is we are going to apply 96 different convolutional filters to this image. And that's going to produce 96 outputs. So the big thing about convolutional neural networks is that they have convolution. And then, you know, they've got some sort of other operations to push the data through the network. But you can imagine you could create a network differently. Okay, you don't need to do all this convolution stuff. You could just have something like this, where you pass an image into dense layer, okay, and then you have another dense layer, and then you make a prediction. So that would be another type of multi-layer neural network. But I guess what distinguishes this type is the convolutions.
So is it that these filters are more proven to give you the right results, or?
Yeah. So if you have spatially correlated data, like in an image, it makes a lot of sense to use a convolutional neural network. And you could also do it in time as well. So you can have temporal data, and then you could have 1D filters that you could you know, construct a CNN with. Or even 3D data, like you have an MR image or a CT image, it's 3D data. You can build three-dimensional convolutional kernels and train a CNN that way. Yes?
How important is the architecture? Like you mentioned, like data, you've got to have good data, but
Yeah.
like it seems like with the CNN, it's like go through the MATLAB sheet and it's like, oh, just whack a few convolutional layers in and whack a few other layers and it should work. Like, do 9 out of 10 networks work? Or like
yeah, as long as your you know, your inputs have the right number of channels and the right number of outputs, you know, it works. Otherwise, your code will crash. Okay, sometimes. But if your code runs, your network probably will produce some result, and it might actually be a good result. But you know, since like AlexNet came out in 2014, you know, people have been looking at these networks and trying to see, you know, how can we be better. And so there's been a lot of innovation in terms of network architecture. I'm going to show you some ways in which you can improve on this type of architecture to get even better results. So the architecture does matter, but even with a simple architecture, you can get a good result. Yes?
Just check with this
So the answer is yes. So be careful when you see something like this, or even you got somebody like me up here talking. When you say like a 5x5 filter here, what that means is it's 5x5 in this dimension, but it's 96 along this dimension. Okay, so you're filtering across all of these channels. And same thing here. Now we're filtering across 256 channels. So, so yeah, that's quite important because you want to aggregate that data through all of the channels. It's a great question. Okay, so what I'd like to do now is talk a little bit about noise, because what I really want to do is talk about denoising using convolutional neural networks. So when it comes to noise, we've all seen it. In fact, it's unavoidable with data capture. And when you're dealing with images, denoising really is a fundamental problem. Now, it's quite important to know how the noise is formed. In fact, this is what we do at Huawei all the time. We're talking about noise sources and how to model them properly. Now, you'll recall from lecture 2, when you capture a photographic image, it's captured using this bear pattern, right? And in this raw image, there are two types of noise. There's the shot noise, which is signal dependent, and there the noise is actually proportional to the intensity because it relates to the arrival process of photons on the sensor. There's also read noise, which is signal independent, and this is generated by electronics when the sensor is read. So anyways, you can try to model these different noise sources and then try to build a denoiser that works on the raw image. But the thing is, processing raw images is kind of an atypical thing to do. What's more common is that you'll get an image that's come from your camera, and then you want to denoise it. But actually, the data is going to go through a lot of processing in the camera itself. It's going to go through high dynamic range compression and demosaicing and all this stuff. So the noise becomes very difficult to model properly in the RGB domain. So typically what people assume is that the noise is Gaussian. And by the central limit theorem, that's not a bad assumption. Okay, so if you want to denoise an image, actually there are loads of ways to do it. And people have been working on this for forever, okay? In fact, you might remember, even in this module, you were doing low-pass filters a couple labs ago. So here you can apply low-pass filters going to remove noise, but it's also going to blur your edges. So that works, but it's not optimal. There are other types of image filters. There's the median filter, which is good at removing impulsive or spiky noise, like if you have individual pixels that are somehow standing out. A median filter is a great way to process that. More recently, there's techniques called anisotropic diffusion and bilateral filters, which are designed to apply nonlinear techniques which blur along edges but not across them. If you blur across an edge, then the image looks blurry. But if you blur along the edge, actually the image looks pretty good, and it's an effective way to reduce noise. There's also this thing called non-local means, which exploits the self-similarity of images. So in an image, there's a lot of pixels that look like other pixels in the image. So what this thing does, it basically does some patch matching, and it finds for an individual patch other patches that are like it, and then it uses that ensemble to reduce noise. And then there are other things like wavelet denoising, and then there's this thing called BM3D, which is actually a very well-known algorithm which combines non-local means and wavelet techniques in order to denoise. And most of these things are actually in MATLAB. You can give it a try if you want to. But what I want to do today is talk about deep learning, and what I'd like to do is explain how you can build a denoiser using a convolutional neural network. And in fact, one of the best known approaches to denoising an image is DNCNN. This stands for the denoising convolutional neural network. So DNCNN, it makes a few assumptions. First, it assumes that the noise is Gaussian distributed, okay? But it is possible to use other noise models. It assumes the noise is additive, and it assumes the noise is easier to estimate than the clean image. So in DNCNN, we've got a quite simple mathematical model here. what you've got is an image that you observe. Okay, we're going to call that Y. That might be the image that I take with my camera. That image is represented by a clean image, okay? And then there's this additive noise, okay? So in my image, I've got noise, but there's also a clean image. Here, I'm just decomposing that into those two different components. Okay, so here's the architecture for DNCNN. It's actually really simple. So here, what you're going to do is you're going to pass in a noisy image, okay? And what you're going to produce is the noise. Okay, that's kind of an interesting thing that DNCNN does. So this image comes into this first layer, okay? And what it's doing is convolution and then ReLU. So the convolution, it's using 3x3 filters, okay? And if I have a grayscale image, then you know, it's 3x3x1. Or if I have a color image, it's going to be 3x3x3 because I'm going to filter across the red, green, and blue channels. Okay, so once I've done that, then I've got these feature maps. And in fact, I'm going to have 64 of these feature maps. Okay, so I'm going to have 64 of these filters produce 64 channels. And then I'm going to put all of that through ReLU. Okay, so essentially I've filtered the image 64 times, and then I've put all of the outputs of those convolutions through ReLU, which gave me a nonlinear activation. Okay, so that's what I have here coming out of this green layer. Does that make sense? So it's just convolution of ReLU. Okay, then the next thing that happens is I put it through another layer, which is nearly identical, except this one has batch normalization. Okay, so I've got convolution, batch normalization, and ReLU. And again, this is going to take 64 channels in, and it's going to output 64 channels. Okay, and again, I'm using 3x3 filters, actually 3x3x64, because I'm filtering across all the channels. Okay, you can kind of see where this is going. Okay, I've got lots of these. I keep going. I have D of these layers, okay, till I get to the end, okay? And at the end, what I want to do is take all of the feature maps that have come out of the last, well, penultimate layer, and I want to estimate the noise. So here I'm going to have 64 channels coming in, okay, because that's what this layer outputs. And then what I'm going to do is actually just have C output channels, where C is 1 if it's a grayscale image, or 3 if it's an RGB image. Okay? So here it's a grayscale image, so C is 1. So essentially what I've done is I've taken this original input image, I've pushed it through this network, and I've estimated the noise. Does that make sense? So that's one thing that DNCNN does that's quite interesting. It's actually estimating the noise rather than the clean image, because a different way to make this network would be to actually estimate the clean image instead. But instead they estimate the noise, so we can model the noise using this equation, okay? So Y is my observed image and X is my clean image, so B is the noise. And so this network, calling it R because it's a regressor, it takes a noisy image in and it produces the noise. You with me? So this is a regression, and we're going to predict a floating point value at every single pixel. Does that make sense? Okay, so that's the architecture for DNCNN. Now, in order to fully characterize it, we need to talk about the loss and how we're going to train it. So in DNCNN, what we want to do is estimate the network parameters, which will minimize a loss. And that loss is formulated as the difference between the predicted noise image and the ground truth noise image. Okay. So here I've got the predicted image, that's this R. Okay, so I'm going to pass in my noisy image, and theta here are the network parameters. Okay, so I'm going to optimize the network parameters to minimize this loss. So this will give me my predicted image. Over here is the true noise image, okay? Because I've got the observed image, I've got the clean image. If I subtract the two, I've got the noise. So what we're going to do is we're going to compute the difference between these two images, essentially. And that's denoted here by this Freybenet score. Okay, yeah.
For your ground truth, have you got images that you put fake noise on that is distributed in the same way that you think the real noise?
Yeah, great question. So that is how you do it. So here, if you assume the noise is Gaussian, then you can take a clean image and add noise to it using, a Gaussian noise generator. So that's exactly what's being done here. Okay. We're here.
By batch normalization, we're using a group image.
Yeah, for a batch. That's right. Yep. Okay, so we're just going to compute this for every pixel, and and here's the number of training images. So here's the loss, okay, and the loss is a function of theta. Theta here represents the weights in my network, okay, so that includes all the convolutional kernels, okay. Those are theta, and batch normalization has some weights I need to learn as well. So all of that is represented by theta, and the goal here is to update theta so that the loss becomes minimized. And that's what the backpropagation is going to do. So to train this thing, what we're going to do is we're going to take clean images, we're going to extract 50 by 50 patches, and we're going to add noise to them using a synthetic noise generator. And in the DNCNN paper, they actually look at different ways to train this. So in DNCNNS, they have specific Gaussian noise level. For example, they assume that the noise variance is 15 or 25 or 50. That works for that very specific noise level, but in general, you might not know what the noise level is. So they also develop what they call a blind denoiser, and this is trained for Gaussian noise over a very large range from 0 to 55. Okay, so 0 is like no noise, 55 is like an extremely noisy image. And they also have a color version of this. Now, in their network, they set the network depth D to 20. Okay, that's the number of these layers here shown with the blue kind of color. And they experiment with different ways to optimize the loss using, say, stochastic gradient descent or Atom. And they're using the MapCompNet library in order to train this thing. Okay, MapCompNet is a library that you can use in conjunction with MATLAB to do deep learning. Okay, so what's interesting about DNCNN is that it doesn't have any dense layers. Okay, it's only got convolutional layers. It's got some batch normalization, but the thing is, the weights are they're in these layers, and they can be applied to any size image. Okay, so this type of network is said to be fully convolutional because it doesn't have any dense layers. What that means is you can train the network on small patches, like 50 by 50 patches. You're going to learn these convolutional kernels that are in the convolutional layers. But then in inference time, you can change the size of the input. So now you can use an image that's 100 by 100 or 1,000 by 1,000 pixels, and you can put it through your network. And as long as it fits within the GPU memory, you can do inference on that and remove the noise. So anyways, once you estimate the noise, okay, that's what this network does, then you can subtract it from the observation, and that will give you the clean latent image. So this is how DNCNN works. You estimate the noise and then subtract it off from the observed image. Does that make sense? Okay, so we talked about DNCNN. Hopefully you have a feeling for how it works. But how do you know if it produces good results? Well, this gets into evaluation. Okay? How do you evaluate a denoising technique? In fact, how do you evaluate most of these sort of image-to-image techniques? A very popular technique is called PSNR, and essentially this is going to measure the peak signal-to-noise ratio, which characterizes how similar the estimated result is to the clean ground truth. Okay? So here, let's say image 1 is my estimated output from my network, and image 2 is my ground truth. Okay? Essentially, I'm just going to look at the difference between the two of those and square it. Okay? So this is like the mean squared error. Okay, so I'm going to divide by the number of pixels. And then I can just put it into this formula where R squared is the maximum possible value. like 255 for a standard image. And essentially, when the PSNR increases, then I'm getting better results. So for PSNR, higher is better. Okay, so let's check out some results. This is for DNCNN, and what we're doing here is denoising a pretty severely degraded image. Here the standard deviation is 50. You can see the noise level is very high, and using DNCNN, we're able to get some pretty nice results. I mean, you can tell the noise level is greatly decreased. One of the challenges with denoising is to remove the noise, but not blur over any edges or high frequency content. And DNCNN is doing a pretty good job here. So the PSNR here is 26 compared to the input, which was 14.7. So it's really improved the PSNR. And even compared to BM3D, which is a very good traditional technique, DNCNN is doing better. Here's another example, again, at a standard deviation of 50 for the noise that's added to the photo. And hopefully you can see DNCNN is giving a very clean result, better than BM3D. And that's also corroborated by the PSNR level. Here's a color example. We've got the zebras in the field. The standard deviation also very high, 45. And if you compare BM3D color version to DNCNN, you can see there's more denoising and the content is well preserved. So you can actually do DNCNN in MATLAB. In fact, it's built into MATLAB. It's invoked using this function called the noise image. Okay. So in order to use this, okay, you're going to want to first load a neural network, and that's here. Okay, net equals denoising network DNCNN. Once you've done that, then you can, apply it to an image. Here we're adding some noise to an image and then denoising it using the DNCNN approach. And here's what you get. Okay, so you can do this. It's in MATLAB. It's super easy. Okay, any questions with that? Okay, what I'd like to do now is switch gears a little bit and talk about image super resolution. This is also a super interesting problem, and I think Slabaugh introduced it a few weeks ago. Essentially what we want to do in super resolution is take a low resolution image, okay, it's kind of got a small size, and we want to blow it up, make it bigger, okay? Now this problem, it comes in different flavors. What we're talking about here today is single image super resolution. So given a single image, okay, I want to produce a higher resolution image. And so I might create a network that does this. And what you want to do is outperform standard techniques like bicubic interpolation. Okay, if you used IM resize in MATLAB, it's doing this type of approach. Can you do better using a deep network? And you can always compare it to the ground truth when the ground truth is available. Another flavor of this is multi-frame super resolution. Here you're given a set of images, like from the video sequence, and you want to produce a high resolution image. Okay, this is an important problem because often you really want high resolution detail, but you don't have it. So this comes up in things like surveillance, forensics, satellite imaging. And you could just buy a better camera and use a high-res camera, but sometimes that's not an option. So here what we're trying to do is overcome the inherent limitations of the sensor. So this problem is ill-posed in the sense that the solution is not unique. If I gave you this really low-res image, could you tell me what the high-res version of it looks like? Well, it's kind of hard, right? In fact, there are lots of possible high-res images that will produce this low-res image. Okay, so there's no unique solution to super resolution, but it doesn't mean we can't work on it. Okay, so one of the first approaches to super resolution using deep learning is called SRCNN, which stands for Super Resolution CNN. And essentially what it does is it takes this low resolution image and it first interpolates it to the desired resolution using bicubic interpolation. Okay? So we take this low-res image, we just instantly upsample it to the desired resolution. Now by doing this, actually this image, it doesn't look very good. Okay? It looks a bit blurry. So what we want to do now is learn a correction to this image, which produces a high-resolution image that has all the crisp detail that we want. And the way SRCNN does this is it first applies some convolutional filtering to the image. Okay, so here we're going to use 9x9 filters, and we're going to have 64 of these filters produce these 64 feature maps. Okay, and so after convolution we do ReLU. Okay, so very similar to what we just saw in DNCNN. Then the next thing that happens is we filter those outputs using 1x1 filters, which are going to filter across the channels, okay? And that's going to give us 32 feature maps. And then we're going to reconstruct the high resolution image here, producing a 3-channel output, okay? So you can see this is kind of like DNCNN, but actually there are only 2 layers in SRCNN. So this is actually a pretty small model for deep learning, but nonetheless, this is how it works. Okay, so in SRCNN, we're going to minimize the loss, and this loss is pretty similar to what we saw before. Here, the predicted image is F, okay? So given the observation Y and the network parameters, we can make a prediction F. And then we're going to subtract it from the ground truth. It's called X here. And then we're just going to square the difference between the 2 images. So this essentially is the L2 loss, if you're familiar with that. So anyways, here are some results. On the left, you have the original image. In the middle is bicubic interpolation, and on the right is SRCNN. So essentially, SRCNN is learning how to improve from a bicubically interpolated image. And I don't know if you can tell, but hopefully from where you're sitting, the detail in the SRCNN result is crisper, and indeed the PSNR is certainly higher using this approach. Here's this horse again, looking at the texture on its body. Again, the dB is about 3 dB higher using SRCNN. So this technique is effective based on the objective quality measure. Okay, any questions with that one? What I'd like to do now is talk about another super resolution network. This one's called VDSR. So VD stands for very deep, okay? And here what we're going to do is extend SRCNN by using 20 convolutional layers. So this is getting more like DNCNN. And what we're going to do is by using the deeper network, we're going to have an increased receptive field, okay, which allows more contextual information to be exploited. So in VDSR, the layers, for example, if we have 3x3 filters, okay, if I apply a 3x3 kernel to this part of the image, it relates to this pixel, okay? And if I apply a 3x3 pixel or kernel to this part, it relates to this pixel. So this pixel in layer 3, it's actually seeing all of these pixels in layer 1, okay? So you can imagine as you make the, increase the number of layers, you're increasing the receptive field because the pixel over here sees a very large part of the original image. So we can make these deep networks, but the thing is, when they get really deep, then you start having problems with training. Okay? You can have these problems called vanishing gradient or exploding gradient. Vanishing gradient is when the gradients just go to 0 and you can't push any gradient back through the network. Exploding gradient is where your gradient just gets huge and your network training becomes unstable. So what VDSR is going to do to deal with this problem is provide a global skip connection. I'll show you that on the next slide. This allows you to learn a residual or a difference image rather than a super resolved image. The other thing VDSR does, which is quite interesting, is it super resolves the luminance channel, and then it, because the human visual system is more sensitive to intensity of the color, then it just applies the color onto the image. So here's the architecture. we're going to take a low-res image, and like SRCNN, we're going to upsample it to the final resolution. Okay, but this image is very blurry, it's missing a lot of high-frequency detail. Then we're going to put it through a number of convolutional layers, 20 in this case, and the convolutions are 3 by 3, and we're going to have 64 channels out. Okay, so this is very much like DMCNN, to the point where we get to this residual, and because of this global skip connection, okay, what's happening is I'm taking the original image and I'm fast forwarding it to the end of the network, okay? And I'm putting a plus here, so I'm going to add the original image to what's ever estimated by this network. And by creating this global skip connection, what happens is I only need to learn the residual, the difference between this image and that image, in order to produce my high resolution output, okay? So this is how VDSR works, and we're going to minimize the mean square error, just like we saw in the other techniques. Does that make sense? So in the VDSR paper, they look at the value of having more layers in the network. And they try to for different upscaling factors, like if you're increasing the resolution by a factor of 2 or 3 or 4. And pretty much in all cases, the network does better when it's deeper. Okay, so here are some results. What you've got here is the ground truth. Here's the result using SRCNN, so we just talked about that a few minutes ago. Here's the result using VDSR. So hopefully you can tell the details a bit more crisp, and the PSNR is increased as well. Here's another example of some animals in the field. Again, get more crisp detail using VDSR. So the good thing about VDSR is that it produces higher fidelity results. The downside is that now we have 20 layers, and so it's going to be slower to run, both training time as well as inference. And in fact, you can look at this. Here's the PSNR on the left side of this plot, and on the right is the runtime. Okay, actually, so the PSNR is pretty high. They claim their method is fast, but actually, it's you're going to pay a price in terms of all of those layers processing. Okay, so you can do this in MATLAB, believe it or not. So in MATLAB, actually, there is a link here. You can check this out. It talks about building VDSR yourself using MATLAB's deep learning tools. And I'm not going to go into all the code here, but essentially what you can do is create a network that has 20 layers. You can have an input layer, then you have all these, here's your convolutional layer, and then for all the intermediate layers, you do convolution and ReLU. Okay, that's what we like that, convolution, ReLU, etc. So you come out of here, then you do another convolution to estimate the final result. Okay, and then you can train this network. So you can do this in MATLAB, and if you're interested, you can follow this tutorial. Okay, any questions with that? Okay, I want to do one more, and then we'll take a break. So yet another network for super resolution is called EDSR. EDSR stands for Enhanced Deep Super Resolution Network, and it has a couple different twists compared to the ones we just looked at. So EDSR is going to incorporate these things called res blocks into the architecture, in addition to this global skip connection. And I'll show you what a res block is on the next slide. The other thing that it's going to do, instead of just taking the low-res image and instantly interpolating it using bicubic interpolation, instead, EDSR is going to process the low-resolution image in the low-resolution size. So most of the processing is done in low resolution. That way, the network is faster, and also bicubic interpolation, it creates a bunch of artifacts. So why start off with a compromised image? Let's not do that. So it does most of the processing on the low-res image, and then it has an upsampling layer to create a high-res image. It also uses a different loss. It uses L1 instead of L2. The network is deeper and wider. Okay, so we have 32 of these res blocks and up to 256 channels. The other thing they do is super interesting is they use a self-ensemble. So what they do is they pass the image forward through the network at inference and it gives them the result. But then they also rotate the image. It's like you can rotate it, 3 other ways. Push those rotated images through the result, and then you rotate back to get another output. So you can imagine by rotation, you can have 4 different versions of the image. They also consider flips as well, so you end up with 8 versions of the image, pass all 8 images through your network, and then you can average all of the 8 inferences together. That actually does better in terms of PSR and other things. So this algorithm, it actually won. There was a competition for super resolution quite recently, 2017. This algorithm won that competition. So the way this thing works is you take your low resolution image and you put it through convolution, and then you have this thing called a res block. And we've got up to 32 of these res blocks. And then here we have this global skip connection like we saw in VDSR, except here we're operating on the low resolution of the image. Okay? Then what we do is an upsample. So we're going to upsample to the desired resolution. Maybe I want an image that's 2x super resolution, 3x, 4x. That's happening here with the upsample. And then we have a final convolutional layer to estimate the high resolution result. And this just talks about the upsample. So this network has res blocks. And a res block, it performs residual learning, that is learning of a difference. Basically, residual relates to a small change of information flowing through the network, so it's easier to learn. And in fact, res blocks were the key idea behind the ResNet architecture that won the ImageNet challenge in 2016. Now, in a res block, essentially you've got the data coming in, okay? And what you do is you run it through a bunch of layers. Here I have convolution, batch normalization, ReLU, another convolution, another batch normalization, okay? And then I just add what comes out of this to the original input, okay? So what this is doing is learning a difference or a residual compared to the input XL. Okay? So this is the original res block that was in this paper. But what EDSR does is it removes the batch normalization layers, okay? So it's pretty much the same thing, except there's no batch normalization. The other thing is, oh, sorry, go ahead.
So, with that addition,
Yeah.
if that helps learning, couldn't the weights learn to do that by themselves?
Yes.
If it was useful?
Yeah. So a different way to do this is you don't have the addition, right? And you don't have this connection. So basically, the data comes through here. It goes through all of this stuff, and then you keep going. So that's certainly a valid option, and you can design a network that does that. The thing is, there you've got all of the data is going through all of these layers, okay? So when it comes time to train this thing, we're going to have to backpropagate all of the gradients only through this channel, okay? And you can imagine with all of those layers, it might become a problem in terms of vanishing gradient or exploding gradient. So instead, when we're backpropagating, we are backpropagating through all this stuff, but we're also backpropagating through here, okay? And this is a very short connection. So that's why res blocks help with training.
So is that helping the loss be propagated back to the next one behind?
Yeah, that's right. That's right. Because we're going to put this into this big network where we have like 32 of these things. So if we didn't have the residual part, then we'd have 32 times 5. You'd have like 150 layers. It becomes very difficult to train a network like that. Good question. Okay, why don't we take a break here, and we'll come back in 10 minutes, and we'll talk a little bit more about EDSR and get into some other problems as well. Sure, we go.
Because it changes the song. So because of these lines where layers have classification, yes, opposed to classification, so where the cat
So you design the measure, you say how to sell the output change. And so you say 55. Then your let's say you're getting something got put all of those in the memory at the same time. So usually what you do is you randomly grab a subset of those and put them in the batch. So maybe that's called and you put that through your method. And when you're using batch normalization, what it's going to do is it's going to take that batch, it's going to normalize it by using but the batch selection is going to self-select.
Intuitive understanding of it. Basically, in screwdrivers, and that really for a while. It seems to have a whole bunch of things. Instead of stacking the layers on top of each other, they have like 9 layers of convolution, but they all go from the input to a layer of convolution. Whatever they have there, they do a maximum the whole because they're templates, and then they just all catenate back together, almost like an embeddment that they so they just have big line trees up. And I think what convolution in a picture, intuitively I kind of feel that every time you go for a convolution, sure you're kind of expecting a feature, but you're also discarding some others which you might not. So why don't we say, for example, when every day it's an extra user, and then that set of features be passed like that, either they go through logistics.
We're going to learn more abstract and then the next
Have like a network where very deep racing in your find each other even in one day your back together. that's the first setting, so it's review, and the last is and then this is the secondary second one.
Yeah.
But then where do these
So what happens here is when you use an export, And one of the important features of ESR is that it has this res block approach. And another really important feature in EDSR is upsampling. And in fact, there are loads of ways to do upsampling, as I mentioned before. What EDSR does, it uses this thing called a shuffle upsample. And this is an interesting way to upsample because it's actually a way to learn upsample. Essentially what this thing does is it creates extra feature maps, okay? So, and those are depicted here in these sort of colored, multicolored outputs. And what it's going to do, it's going to shuffle all of these pixels into a higher resolution image. So you can see this purple pixel, it appears here. And then this next one appears a couple pixels over, etc. And that's going to be interleaved with the blue pixels and the yellow pixels and the red pixels. So all of those pixels are going to be, kind of shuffled into this image. And in fact, you can also learn the upsampling by learning the feature maps as well. And this was a very interesting paper when it came out. It was by these people, Shi et al. They're actually from a company called Magic Pony. And I don't know if anybody remembers this. It's not too long ago. These guys were at Imperial College London, and they sold their company for $150 million to Twitter. Okay? So now Twitter owns Magic Pony. And their key feature, their key technology was a way to upsample images. Okay, so anyways, in EDSR, if you put that network together and you train it, you can get some really impressive results. Here, for example, we're going to kick it up to 4x super resolution now. Okay, so we're really super resolving. Here's a little patch. Okay. Here's the high resolution ground truth, so we want to reconstruct this image. We use SRCNN. It works, but it's not great. It's quite blurry. Here's EDSR. Okay, we covered that one a few minutes ago. And here's EDSR. Okay, so now EDSR is really outperforming VDSR. Here's another example with a cat. Okay, we're going to look at its whiskers. Again, EDSR doing a really nice job in getting real high frequency content. It's not perfect. It doesn't look exactly like the high res image, but really high quality super resolution. Okay, any questions about EDSR? So EDSR is really one of the state-of-the-art algorithms right now for super resolution. So you're learning the latest and greatest. But in the last year or so, people have started questioning the purpose of super resolution. In fact, what people have noticed is that you can make networks like EDSR that are really good at producing high PSNR. Okay? They minimize the L2 loss. But the perceptual quality might not be as high as you'd like. In fact, sometimes the reconstruction accuracy, it's at odds with the perceptual quality. And this is a good example. So here I have an image. I've done nearest neighbor interpolation, which is like the sort of worst form of super resolution. Here's method 1, okay, and it's got a PSNR of 25, 85. Here, method 2, this actually has a lower PSNR. It's 22.7. But, I mean, I think most people would agree that the image on the right looks better than the image on the left. Okay. So this gets into the question of how do you measure the quality of a super resolution algorithm, and is PSNR really the best approach? So what has happened in the last year or so, people got really interested in trying to improve perceptual quality rather than reconstruction accuracy. And in fact, you can kind of plot the reconstruction accuracy along this axis. Okay, so normally you want to have high accuracy. Sorry, going this way. And you want to have better visual quality, so it's going down. So ideally, you're going to be somewhere down here where you have high visual quality and high reconstruction accuracy. But there are really sort of two camps here. There's the camp that has EDSR, where you actually do very well in terms of mean square error, PSNR, but actually the perceptual quality might be a bit low. There's another class of techniques that actually try to maximize the perceptual quality instead. So they're kind of going for a different target. So if you want to do perceptual super resolution, a good approach is to use a GAN. And you might have heard of GANs before. It's called a generative adversarial network. And a GAN actually has two networks. Okay? There's one network, it's called a generator, and it, in this case, is doing super resolution. Okay, so it's the things we've already talked about. The generator is taking a low resolution image, okay, and then it's putting it through some CNN, which produces a output. Okay, so this could be EDSR, for example. But in addition to that, a GAN also has a discriminator. And the discriminator is trying to decide if the image is real or fake. What I mean by real is it's a real high-resolution image. A fake image here is an image that was started off as a low-res image, and it went through a generator to produce a high-resolution image. Okay? So the discriminator wants to know if it's a real high-resolution image or if it was generated by some algorithm. So when we use a GAN, what we're going to do is train these two networks jointly so that the generator, it tries to produce very realistic images that confuse the discriminator. Okay? Discriminator, it doesn't want to be confused. So it's trying to be a really good detective, if you will, and try to figure out which of these images is real or fake. Now, initially when you train a GAN, the weights are, kind of initialized, usually from random weights. So initially the generator is terrible. It's producing really bad outputs. But the discriminator is not very good either. So it's producing misclassifications, okay? But that's okay. You're going to take the error from the discriminator, you're going to backpropagate it through both of these networks, and both of them are going to improve. Okay, so as time goes on, the generator gets better and better at generating images that look like real high-resolution images. Make sense? Okay, so the reason why we might be interested in GANs, especially for super resolution, is that because this problem is imposed, there are actually a lot of high-resolution images that can represent low-res. And this mean square error or L2 loss, it actually can produce an average blurry result. And that's kind of visualized here in the cyan box. Okay, you took all of these possible solutions and you averaged them together, you might end up here somewhere in the blue box. But a GAN can actually help because it can hallucinate high frequency details and it can produce a more natural looking image that puts you on this manifold of realistic looking images. Okay? And in order to do that, we're going to have this adversarial loss, which is going to be used to train both the generator and the discriminator. Okay. So the latest and greatest technique for super resolution is called ESR GAN, and it's designed to produce perceptual super resolution. And it uses a GAN. This technique, it won the 2018 super resolution competition. This one was designed for perceptual super resolution. And so this just happened probably 6 months ago, so this is super fresh stuff. So ESR GAN, it has a couple of modifications to improve quality. One thing it does is it uses residual blocks and dense blocks in a structure they call residual in residual dense block. Just a bit of a mouthful, I'll show you the next slide. The other thing it does is it tries to use a perceptual loss computed on features before ReLU, so pre-activation. And the reason why you might want to do that is because ReLU, it sets all the negative values to 0, right? So when you get further down in the network, actually the feature maps become very sparse. So by using pre-activation, you can have a more dense or fine computation. Okay, so here's the architecture for ESR GAN, and what we're looking at here is the generator. Okay, the generator is the one that's generating, taking low resolution images and making them high res. And if you look at this, actually it doesn't look that different from EDSR. Okay, so we're going to take the low res image, we're going to convolve it. Okay, we're going to get some feature maps. And then we're going to put it through a bunch of basic blocks. Okay, in EDSR these were res blocks. In this paper, they're basic blocks, and I'll describe that in just a second. And this is all operating on the low resolution version of the image. Then we do some upsampling, a couple convolutional layers, and then we predict the high resolution image. So from 10 feet away, this looks a lot like EDSR. Okay? But the differences are here in the basic blocks. In EDSR, we use res blocks, okay, conv, relu, conv, then we did this add. In ESRGAN, instead, we've got these dense blocks, okay? And in a dense block, what you do is you have a conv and relu, okay? But instead of just taking that output and feeding it directly into the next layer, you do that, but you also skip over this, okay? That's what this orange arrow is. And so you feed two sets of inputs into this next layer. So it's getting, this layer is getting what's coming out of this leaky relu, and it's getting the input before. So by doing this sort of leapfrog, we end up with two sets of feature maps, and then we put them through these layers, okay? And then it kind of goes from there. So this layer, it's actually going to get even more feature maps. Okay, it's getting the one from the beginning, it's getting the one from here, and it's getting the one that comes out of the second pair, and so on. So when you get over here, we're out feeding in loads of different feature maps. Okay, they're all concatenated together, and then we do a final convolution to come out. Okay, so this dense block, actually, it was a paper that came out in 2017, I believe, and it won the best paper prize at CVPR. So this was a big innovation because you got really good results using this technique. So anyways, they put these dense blocks together, and they also have some residual learning here as well. So the input gets passed through, and then it goes through a dense block instead of a res block. Okay? This might look a bit exotic, but people are trying to push this technology as far as they can, so the networks are getting more complicated.
You mentioned multiple losses dealing with perceptual quality.
Yeah.
How do you measure perceptual quality loss?
Okay, good question. Actually, I think that's my next slide, so thank you. So how do you measure perceptual loss? There are different ways to do it. In this paper, what they do is they take the image and they put it through VGG19. So I think Slabaugh talked about VGG19. That is an image classification network. But when you put that image through the network, it's as it goes through the network, it's producing loads and loads of feature maps. Okay? So what you can do is you can take the image, okay, and put it through VGG19 and get these feature maps. That's denoted by phi in this equation. Okay? So you can do that for the generated image, that's G here, and you can also do it for the ground truth image. Okay, so what you're doing here is instead of comparing the ground truth image to the generated image, you're going to compare feature maps from VGG19 for those images instead. Okay? And by doing that, you're actually comparing more abstract versions of the image. You're not comparing the images directly, you're comparing like abstract versions of the image. And it's been shown that especially as you get further into the VGG network, you're learning more abstract features, more abstract representations of the data. And so this relates more towards perception rather than exactly matching pixel to pixel. Okay? When you use an L2 loss, you're matching a pixel to a pixel. Here you're matching more abstract features to abstract features. And so this is a bit more translation invariant. Does that kind of make sense? So that's the perceptual loss. There are actually three losses here. There's also this generator loss that's coming from the adversarial component, and that's denoted here. And I'm running a little low on time, so I'm not going to go into all the gory details here. But essentially, this relates to the generator. It's trying to confuse the discriminator. Okay? So the generator wants this term to be high and this term to be low, because this relates to, discriminator wants this term to be high because this term relates to fake data, this data relates to real data. And so basically this is doing the game between the generator and the discriminator. And then they also minimize the L1 loss. So this will match pixel to pixel in the generated image and the ground truth image. Okay, so when you put all this stuff together, you've got ESR GAN. And this technique does some things that are pretty remarkable, actually. If you look at this result, on the left is the ground truth high-res image. Here's by cubic interpolation, SRCNN, EDSR, and here's ESR GAN. Okay? Now, if you look at this carefully, you'll see that there's a lot of freckles and things on her nose, but they're different than the real freckles on her nose. Okay? So what this network has done is it's hallucinated some of this high-frequency content, but it did it in a way that's very realistic because this type of image is going to confuse the discriminator. And honestly, it probably confused most people as well, unless you knew exactly where all her freckles were on her nose. Here's another example of this building, okay? And here you'll see there's a lot of detail in this image, but actually maybe some of that detail isn't totally real. But that's okay. Perceptually, this image looks pretty good. So this is how you can use a GAN to actually almost like hallucinate high-frequency content. Does that make sense? Yes?
So I guess the problem with that is around, like, if you are going to use it for any of those things you mentioned, like surveillance or something like that, then it's not really.
Yeah, it's a good point. So you need to be careful when you're using these things. Maybe like in a surveillance application or medical imaging, you don't want to just start hallucinating pixels, But if the goal is to produce something that looks good, then maybe this is a good choice. So we're actually exploring these things where I work, how to use GANs and how to use them effectively. Okay, any more questions about super resolution? So hopefully through that session, you've got an appreciation of how deep networks work in terms of designing architectures, in terms of creating a loss, how you go through from one super resolution network into another, how the field has evolved. And hopefully you feel maybe slightly empowered to try to make your own super resolution network, maybe implement one of these things. It's not that hard, honestly, it's not that hard. Yeah?
So, quick one. The discriminator is CNN, right?
Yeah.
What could you use for the generator? Is it also CNN?
Yeah, they're both CNNs. So the discriminator is a classifier. And for that, you can use something like AlexNet or VGG19 or your favorite CNN that does image classification. And then for the generator, you want to create a generator that solves your problem. So if we're talking about super resolution, then you want to take a low-res image and blow it up into high-res. If you're talking about denoising, you're going to start off with a noisy image and produce a clean image. So you can use a GAN in any type of these scenarios. It works. So you just have to design a generator and a discriminator. Okay, what I'd like to do now is talk a little bit about semantic segmentation. And here what we're going to do is we're going to label each pixel in the image into one of n semantic categories, okay, like person, car, road, tree, etc. And this will help you, an algorithm understand what is in the image. You can imagine this would be very useful for a self-driving car. So most semantic segmentation techniques use an encoder-decoder architecture. So essentially what you're going to do is you're going to have a bunch of convolutional layers, and you're going to have some max pooling, which is going to decrease the size of the image. Okay? And so this data coming through here is at a lower resolution, and so the network is looking at the image in a more holistic way. And you're going to keep sort of decreasing the size through, say, max pooling operations till you reach some bottleneck, okay? And then you're going to start expanding the dimensions. So this is going to use upsampling till we get back to the original resolution, okay? And so in this encoding part of the network, okay, it's learning what is in the image. So this is what we mean by semantic. I want to know what's in the image. Is it a cow? Is it a tree? Is it grass? But then the decoding side of the network, it's learning where the content is located. Okay, so when you come out of here, you should know at a very fine pixel level detail, what all the labels are. So there are different ways to do semantic segmentation. A very popular network is called FCN, stands for Fully Convolutional Network. And this one, it doesn't have any dense layers, okay? And we're going to train it end-to-end using a VGG style encoder. For decoding, we're just going to upsample. So hopefully you've seen this kind of thing before. This is like a VGG style encoder. We've got an image. It's going through convolution and ReLU layers, okay, 64 channels. And then there's a max pooling operation. That's this blue layer here. And then on the lower resolution feature maps, we're going to send those through more combs and ReLUs, max pooling, and so on. And you'll see the number of channels is increasing. And then what we're going to do is we're going to, when we get to the most coarse resolution, we are going to then make a prediction, in this case into one of 6 labels, and then we're going to upsample. So we're going to upsample, we're going to combine it with the predicted version at this resolution, and same thing here, and then we're going to make a final prediction at the very end. Okay? So this is a way where we can make predictions using encoding, okay? And then decoding is upsampling combined with additions. So the loss in one of these networks, this is different because we are doing classification in each pixel instead of regression. So the loss here is going to be a cross entropy. So maybe we have these different probabilities at each pixel. Okay, here's my ground truth. I can use the cross entropy to penalize any difference between the prediction and the ground truth. And that'll give me an error, which I can then back propagate through my network to update the weights. Okay, so FCN works, and it's a good approach for segmentation. But another approach that's also very popular is called UNet. And UNet is a little different than FCN because it has skip connections that pass feature maps from the encoder side to the decoder side. So in UNet, what's happening is you start off with an input image, okay? And in this case, you run it through 64 convolutions, okay? And that produces 64 feature maps. You can put those through ReLU. And in fact, you can do it again, okay? And that's what you see here. Now, these feature maps are at the original input resolution. What I'm going to do next, I'm going to downsample, okay? So here I've got a max pooling operation, and the feature maps are now at half the size and width of height. And I'm going to run these through more convolutions and ReLUs. And I'm going to keep going like this, okay, until I get to the bottom of this network. And this side of it is the encoder, okay? So I'm encoding the image, and I'm trying to figure out what is in the image semantically. The right side of this network is going to decode, okay? And the way it's going to do that, it's going to apply convolutions, ReLUs, and upsamples, okay? And I'm going to work my way back to the original resolution up here. But what's interesting about UNet is it has these skip connections that will take the feature maps, okay, in this case at the highest resolution, it's going to pass them over to the decoder side, okay? And then it's going to do a concatenation. So the feature maps I have here, they're concatenated with the feature maps I had on the decoding side. This way, I have a lot of fine resolution detail here in these feature maps. They're passed over here. That way, my segmentation map is going to be more precise than if I didn't have these skip connections. Okay? And in fact, on FCN, it doesn't have those types of skip connections. So UNet tends to give more precise boundaries in segmentation. I've got one more technique called ICNet, but in the interest of time, I'm going to skip it. The thing about ICNet that's interesting is that it does most of the processing on a low resolution image in the encoding side. So we end up with really fast results, and we can achieve real-time segmentation. In fact, here's an example. So here's real-time segmentation on the this kitty data set. It's running at 30 frames per second, which is pretty remarkable. So labeling every single pixel at real-time frame rate, which I think is amazing. So in this application, the algorithm, it's labeling each pixel into one of these semantic categories. Now, some quite ingenious people thought, what if we invert this process? Okay, what if we go backwards, where we take a semantically labeled image, okay, something really crude like this, where maybe you just draw it in a paint program. Can you go the other way and create a realistic image? Okay, believe it or not, you can do this. It's amazing, actually. So this is a paper, it hasn't even come out yet. This is coming out this year, CVPR, it's in June. So this is ultra fresh, bleeding edge stuff. Basically the way this thing works is it is using a GAN, okay? And they call their technique GoGAN, strange enough. And what they do essentially is they put noise into a neural network where we have some convolution and Rayleigh layers. And then they have this thing they call a spade res block. Okay? And spade res block, what it does is it takes the semantically labeled image, okay, and it puts it through some convolutions and then does sort of a scaling and an addition along with some batch normalization. And essentially, this overlays the semantic content into the data at this resolution. And it keeps going, doing some upsampling until it gets to the full resolution. And it trains this thing using a GAN. Okay? And this is pretty amazing stuff, actually. I think I've got a video here. So unfortunately, the audio's not working, but what you can see here is they've got sky and water on the bottom. And here he's drawing a mountain, I guess. And as he does that, the image on the right is updating, and it looks quite photorealistic. And you can change, the daytime, nighttime, different kind of styles coming from other images. And this is all interactive and quite real. So pretty amazing technology. And in fact, if you've been reading the news lately, you might have saw this. This was pretty amazing. So there was a GAN that some French computer scientists made, which produced art, okay? And then they had one of their artworks sold at Christie's, and it sold for $432,000. So it's one way to make some money. And the artwork is produced using a GAN, using 15,000 portraits painted between the 14th and the 20th centuries. So pretty interesting things you can do with GANs. Okay, I'm into my quick fire session. I just want to buzz through a couple different technologies and then want to run through the module. So first up is pose estimation. Here what we want to do is be able to identify all the joints of a person, especially as they're articulating and sort of moving in front of the camera. And this is hard for a million of different reasons. There are occlusions, there's symmetry ambiguities, there might be multiple people, changes in appearance, all that stuff. But it doesn't matter, we can put this data through a CNN and have it predict joint parts, joint locations. And in these types of problems, we also typically use encoder-decoder networks. And in fact, you could use UNet. There's another approach called an hourglass module, which is very similar to UNet. But instead of skip connections, it has additional convolutional layers and residual connections. So instead of concatenating, we're adding. But essentially, this is very similar to UNet. And there's this one paper called Stacked Hourglass Networks, which create these things. And rather than just use one, we use a bunch. Okay? And what happens is you pass an image into the network, and it produces heat maps, okay? And you have one heat map for each joint you're interested in. So here, for example, I might be interested in the left elbow, okay? So I'm producing this heat map image telling me where I think the left elbow is given the input data, and so on for the other joints. And if you connect all of those joints together, you can create some sort of kinematic model, right? And then you can, you know, do that frame by frame and sort of track motion through a video sequence. Another problem, optical flow. Okay, we covered it in this module just a few weeks ago. You can use deep learning to estimate optical flow. Here you've got two images, okay? One image at time t, another image at time t plus 1. You're going to put it through some convolutional neural network, which is going to regress a vector at every pixel. That vector is the optical flow. And different ways to do that, but typically also using an encoder or decoder structure. But what's different here is that we have two images that are input, okay? So what we're going to do is pop two images into this network, and we're going to use some shared weights in these convolutional and ReLU layers, okay? And this type of architecture is called the Siamese architecture, okay? Because we have these multiple inputs that are shared, have shared weights between the two different streams. Then we concatenate them, and then we do some more estimation to predict the optical flow vectors. And you know, there have been a lot of people working on this using deep learning techniques. You know, here's a paper from ICCV 2015. People have done it more recently. You know, if you go to any computer vision conferences these days, there's going to be someone there probably talking about optical flow. Another problem you can solve with deep learning is stereo. We covered this as well a few weeks ago. You'll remember the goal here is to estimate the disparity or the shift of pixels between the left image and the right image. And what StereoNet does, this is a paper, it just came out ECCV 2018, just a few months ago. This is from Google. What they're doing is predicting the disparity using rectified images. So we talked about image rectification before. It's basically a warp of the image so that the search for a match is along a horizontal scan line. So basically it's making the polar lines horizontal, okay? And in StereoNet, we also have a Siamese network because we have two images, okay? And we're going to have some shared weights that extract features from those two images. And we're going to look at different possible disparities and put the different disparities into something that's called the cost volume. Then we're going to basically upsample that to produce the final disparity estimation. And this is a very high-level description, but details are in the paper. I was going to do an exercise, but we're a little low on time, so I'm going to skip that. So a few takeaways from this deep learning lecture. So deep learning is a very powerful technique, and it's actually transformed a lot of different fields, not just computer vision, but natural language processing is another good example. You know, in deep learning, what we're doing is we're basically learning a system that can simultaneously estimate features and do some sort of classification or regression. But the main thing is that the features are learned compared to traditional approaches. So by designing a good architecture and training it with a loss, okay, we can update the weights using backpropagation. And if we are doing problems that involve synthesis, like synthesizing texture in super resolution or synthesizing a painting, then again, it could be a good choice. Now, when you're thinking about architectural considerations, first, deeper networks are usually good because they aggregate information over wider receptive fields. They also have more weights, so you have more capacity in your network to learn. The only thing is, very deep networks may have some problems with vanishing or exploding gradients. So to counteract that, you might consider using residual learning, for example, res blocks, which can help with these backpropagation gradients, because there you only need to learn the difference. Encoder-decoder networks are good at extracting global features in usage. In fact, you see these networks for segmentation all the time, but also optical flow and stereo estimation. And if you have multiple inputs, like in optical flow, then Siamese network is probably a good choice. You can have some initial layers that have shared ways to extract features from the data. Now these days there's loads of code online. If you want to do deep learning, you can go into GitHub, you'll find just tons of code, PyTorch, TensorFlow, etc. And this can be a good way to learn. You can take other people's code, you can play around with it, you can see how it works. But these days, it's really essential to have a GPU if you want to do this stuff, because otherwise the training is just unbearably slow. So this is one of the reasons why we don't have a lab tonight dedicated to deep learning. Instead, we're just going to work on the coursework. But nonetheless, if you want to do deep learning, maybe in your individual project, I would recommend it. Deep learning is setting the state of the art in many of these problems. But there are also some limitations to deep learning that you should be aware of. First of all, to do deep learning, you're going to need large data sets. If your data set's too small, deep learning is probably not the right tool. The methods described in this lecture required label data. Okay, so everything I talked about tonight is supervised learning. You can do unsupervised deep learning, like using autoencoders, for example. But often the problems you might want to approach are going to be supervised problems. The algorithms can be complex, okay? It can be very slow to train your network, even with a GPU. And sometimes, pretty much most of the time, your results are a bit difficult to interpret. This leads on to this whole notion of explainable AI, which is a very hot topic right now. But more often than not, you might think of your network as a black box. That being said, there are ways to visualize the features that are coming out of your filters. You can look at the convolution filters themselves. But if you have 64 filters, it might be kind of hard to reason about that. Deep learning is biologically inspired, but it doesn't actually capture the biological mechanisms of the brain, I would say. There's a lot that we don't know about the brain, to be honest. And for deep learning, there actually is some limited theoretical understanding of how it works. People are improving that. There are also hyperparameters. You use 20 layers in your network, 25 layers, how many channels. These kind of hyperparameters require a fair amount of optimization if you want to really get every ounce of performance out of your network. Okay, any questions about deep learning? Yeah.
Obviously architecture you just said there is something which is sort of set by the user, essentially. Is there anyone working on using deep learning to basically learn architecture?
Yeah, great question. So this is called AutoML. And basically what you want to do is use deep learning to automatically make a network so that you don't have to tune all these hyperparameters. It will tell you how many layers you need, how many channels you should have, etc. So this is a very active field of machine learning at the moment. In fact, people are working on this. Any other questions? Okay, what I'd like to do in the last couple minutes is sort of wrap up this module. We've had 10 lectures, and hope you've enjoyed them all. Just kind of a quick recap, we've come a long way this term. So we've looked at things like, image processing, face detection, segmentation, image understanding, features, image warping, image classification, CNNs, augmented reality, optical flow. We've done a lot of stuff in this module. And at this point, I think you've got a good grounding in computer vision. So we've looked at all of these different problems. We've used MATLAB and the Computer Vision System Toolbox as a mechanism to experiment with computer vision, to prototype algorithms, to try different things. And hope you enjoyed working on that. Here's a few people that we've come across. We haven't seen their faces, but here's Michael Jones. He's well known for face detection, right? Using the Viola Jones face detector. And here's Jones. Here's Luminita Vies. She's very well known for level set methods. Takeo Kanade, he's the K in the KLT tracker. So a lot of work in optical flow and really many things in computer vision. Andreas S. is actually a friend of mine, and he invented surf with his colleagues at ETH. Here's Alex Krzyzewski. He's the guy who made AlexNet. And hopefully you can see here, not all of these people are super old, okay? You know, there's like a lot of youthful excitement about computer vision at the moment, and a lot of the innovation is coming from, you know, all sorts of people all over the world. So where to go from here? If you've enjoyed computer vision in this module, well, there's a lot more to be said. There's a lot more to learn. Computer vision is really a very active field. There's lots of research and development. The biggest conferences are really the place to go for the state of the art, kind of see where things are going. So here in the UK, there's a conference called the British Machine Vision Conference, and it's held yearly, and it's pretty easy to get to because it's always in the UK. There's also a European Conference on Computer Vision. It's held every 2 years, on even years. CVPR is an American conference. It's held every year. There's ICCV, it's the International Conference on Computer Vision. It's going to be in Seoul this year, Korea. If you're interested in medical imaging, McKay is an excellent conference to learn about the latest applications of computer vision into the medical domain. And that's one of my favorite conferences. In addition to conferences, there are journals. Okay, there's Computer Vision and Image Understanding, IJCV, and PAMI. These are all great journals that feature state-of-the-art research in computer vision. Okay, so this term you've used MATLAB and its Computer Vision System Toolbox. And as you know, in this toolbox you can do all sorts of cool things, from image classification to OCR, you know, face detection, stereo vision, etc. And at this point, actually, we've been through most of the Computer Vision System Toolbox in this module. MATLAB isn't the only game in town, though. In fact, if you want to program real-time systems, real-time computer vision, MATLAB might not be the best choice. You might instead consider using OpenCV, and you can use OpenCV with different types of bindings. So if you're a Python programmer, you can do that. Or maybe you're a C++ programmer, you can even access it with Visual Basic. So, you know, and this has lots of different, you know, support for different operating systems, etc. So if you've enjoyed what you've done in this module, you could try to expand on what you've learned and start using OpenCV. In fact, some of the techniques that you've used in MATLAB, they're actually calling OpenCV under the hood anyways. There's loads of references on using OpenCV, and in fact, some of them we have free access through the library. If you want to do deep learning, there's many different toolkits out there. We've talked a lot about MATLAB, and MATLAB does support deep learning. In fact, I showed you how to do VDSR in today's lecture using MATLAB. If you want to instead look at other APIs, I would recommend either TensorFlow or PyTorch. These days, it seems like a lot of people are going towards PyTorch because it's a little simpler to use. That being said, there's a new version of TensorFlow where they've tried to make it simpler to use. So the future is hard to predict. But where I work, we all use TensorFlow because it's better for sort of real-time deployment. And you can call TensorFlow from Keras. So if you want to have a very high-level API to do your deep learning, Keras is a good choice. Okay, another thing you can consider is doing some challenges. So there are loads of challenges. They're usually affiliated with major computer vision conferences. And if you go onto the websites for these conferences, you can see what kind of challenges they have. Sometimes they're organized as like a Kaggle competition. You know, you can get involved with that. It's always a good experience to participate. And maybe some of you will go on to actually get jobs in computer vision. In fact, there are a number of students who've taken this very module who are now working as computer vision scientists in industry. I know because one of them contacted me recently. So there are good jobs out there in computer vision. Here's just a teaser to get you excited. Here's a data science position doing deep learning, and here's another job. Salary's actually pretty good, I gotta say. So if you find a good job, maybe you can get a good salary as well. Some of you might be interested in further education. Okay, so there's some undergraduates here. Maybe you'll want to go on and do a master's course. Maybe if you're a master's student, you might want to go on and do a PhD. I've got some links here for you. There's this Find a PhD website. Click on this, and I put the keyword computer vision here. So all you have to do is look at the hits and see who's offering computer vision PhDs. If you take one of these PhDs, you'll probably have to work on a very specific problem because it would be funded by an academic at a university, but you know, they would cover your tuition fees, etc. And if you're looking for jobs in computer vision, jobs.ac.uk is pretty good. There's a lot of stuff in there too. Okay, so that's the end. Hope you've enjoyed computer vision, and on behalf of Slabaugh and myself, it's been a real thrill to be here and teaching this term. Thank you.
Thank you for the great lecture tonight. Thank you for putting all the state-of-the-art, now you're all fresh, you're going for the jobs at $70. So I uploaded a mock exam with solutions, and last week I said lectures 8, 9, 10, and 1 are not going to be on your exam. They will be, because I just needed your evaluation. No, it's the 1st April line. So, yeah, tonight there won't be a lab, but you can stay if you like and work on your coursework. We hope you enjoyed this course, and thank you. Enjoy.